Hey you guys, here's our last installment on chapter 10 in chemical bonding. We are going to talk about molecular orbital theory. So let's look at oxygen. There's some problems with the hybridization theory and the Lewis dot structure theory when it comes to oxygen. Oxygen, we would think that our Lewis dot structure looks good, it obeys the octet rule, but as far as the properties of liquid oxygen, they kind of act a little differently than we would have expected. There are no unpaired electrons, so we would predict it to be diamagnetic. But experiments show that it's paramagnetic, and that actually when you pour this liquid oxygen down through a pretty strong magnet, you get some attraction. And since you get attraction, that would indicate unpaired electrons. So our Lewis dot structure over here seems to have some flaws as far as the idea of everything being paired. Now that is where our molecular orbital theory comes in, and that there are new orbitals. I know we had atomic orbitals, hybrid orbitals, and now we're talking about molecular orbitals. And molecular orbitals are a new definition of orbitals that are over the entire molecule, in which the electrons of the entire molecule reside. So molecular orbital theory is an idea that bonds are formed from interaction of atomic orbitals to form molecular orbitals. So you see, each new idea or theory has its flaws, and then a new theory comes in to explain an observation. The observation being that liquid oxygen is attracted to a magnet, and that should not be the case if we are following this idea of even hybridization would predict this. So we're thinking it's more there must be unpaired electrons, but where are they? So we need to say where they are, but we have to define the where, and the wheres are going to be the molecular orbitals. So the molecular orbitals, there's different kinds, and there's bonding molecular orbitals and there's anti-bonding molecular orbitals. So the idea for molecular orbital theory is to create orbitals that electrons can reside in. Now, in order for these to make sense, we have to make concurrent molecules fit in the model. So let's study hydrogen. Hydrogen is the most, very most studied common molecule and atom. And that molecular orbital theory creates what's called bonding and anti-bonding orbitals. So a bonding orbital must be where bonding electrons are residing. Now, anti-bonding orbitals, there can be electrons in there, but if there are too many in anti-bonding than there are in bonding, or if they're equal number, the molecule will not exist. So in order for a bonding molecular orbital to be created, there must be overlap, and it's a sigma. You see that sigma means in between. So there's electron density in between here. You see this is very cloud-like, and that's because it's following that cloud model that we were looking at for our atomic orbitals. So if there is a constructive interference relationship between electrons that are moving as waves, then if there's constructive, you will get a overlap that makes a bond. If there's destructive, then you will get, it will cancel each other out, and we'll see that here in a second. But a bonding molecular orbital has lower energy and greater stability than the atomic orbitals from which it was formed. Lower energy, see where I'm drawing this, and greater stability from the atomic orbitals from which it was formed. So remember, when things run downhill and their energetics are lower, it's favorable. An anti-bonding orbital would result from destructive interference. These anti-bonding orbitals are labeled with a star, and that's in hydrogen, it's empty. And that's because hydrogen, to make a molecule, has 2 electrons. Each and every orbital can hold 2 electrons. So for it to be a bonded molecule like it is, those 2 electrons must be occupying the bonding molecular orbital. An anti-bonding has higher energy and lower stability than the atomic orbitals from which it was formed. Now the reason for this idea is because there are electrons that are not accounted for in molecules, and those electrons are the core electrons. We don't really know where those core electrons are in hybridization models or in atomic orbital models, But if we can put them in there, it might explain the paramagnetism of oxygen. So there's this constructive and destructive interference idea. These are of the electrons that are actually in the orbitals. So if they are moving as waves and they overlap with each other, they will form, constructively, they will form a bond. And that's what this is showing here. That's that constructiveness of the electrons to overlap in an orbital. But if they're destructive, they will cancel each other out. And then you would get no overlappage and no bond formation. Now that doesn't mean they're not there, but we cannot have all of them in the same place and all of them doing the same thing, because then that would be kind of like a double bond. Now, as far as these interactions, we just did s orbitals. Now we're looking at p orbitals. How can these p orbitals interact? They can interact in a constructive or a destructive fashion. What we're doing right now is we are outlining the model or the theory for molecular orbital theory. We are creating molecular orbitals and we are defining them, and then we're going to use them to explain why a molecule either is stable or it's unstable, or whether or not a bond is going to be a single bond, it's going to be 1.5 bond, a double bond, which would be, you could think of the number 2, double and a half, which you might think of as a number of 2.5, and so on. That's what we're doing now. So you can have constructive or destructive interference. This is a sigma bond. Notice it's between. The electron density is between, and if it's anti-bonding, it's not in between, but it's still a sigma. It's still on the line in between the two atoms. For a pi bond, which is above and below, remember from our previous hybridization theories, that is above and below. That's where the electron density is. If it is a bonding, they're still kind of overlapping, but if it's anti-bonding, they're not overlapping. They're kind of repelling each other. So if you take a peek over here, these are called electron molecular orbital diagrams. And I'm going to ask you guys to draw a diagram like this. This is a molecular orbital diagram that shows where the electrons are and where they came from. So these electrons came from a 2p orbital, and they are now in a sigma bonding 2p orbital that's between the atoms. These are coming from 2p orbitals that are now pi molecular orbitals, and that orbital electron density is above and below, just like in the hybrid. These are pi's. These are sigmas. So this is the definition of the theory. So let's continue to look at how those p orbitals might overlap. We just defined sigma and pi bonding and sigma and pi anti-bonding. So let's think, well, maybe if we have a diatomic lithium molecule, Li bonded to Li. But remember, lithium, if you look at lithium on the periodic table, he is number 3. He has 3 electrons, and so does this guy, for a total of 6. Now, what we've only placed here is 2, so where are those other electrons? Those other electrons, according to this theory, are below here. We have the 1s2 from one of the lithium atoms, and the 1s2, and we also have the 2s2. So if we do a quick analysis here, one lithium atom has 3 electrons, which would be in the 1s. So this one doesn't have any in the p's. So this one would have 1s, and there we go. So what I have just outlined here is one lithium atom and one lithium atom. If they come together, they're going to form some bonding and anti-bonding molecular orbitals. Now I'll show you a better diagram for this later. Right now, this was showing how we would fill these up and how those orbitals are related to each other, bonding and anti-bonding wise. So these general molecular orbital energy level diagrams are just showing us, and I'll show you a template that you're going to use for your fun sheet that you could use to build up and create these molecules and see what bond would occur between them. Would it be a single bond for a bond order of 1? Would it be a double bond for a bond order of 2? Would it be a bond and a half for a bond order of 1.5? This bond order that I'm speaking of, we'll talk about here in a second, is a measure of the strength and length of the bond in between two atoms. So bond order is calculated by knowing, you have to know this, the number of electrons in the bonding molecular orbitals and the number of electrons in the anti-bonding molecular orbitals. And you take half of that. So let's do a few examples to illustrate. In our idea of hydrogen, we talked about hydrogen a second ago. And remember that hydrogen was formed, one hydrogen atom comes in with its 1 electron in the 1s orbital, and the other one comes in with its 1s orbital. And it forms a bonding and an anti-bonding. Now, if it's a bonding molecule and we know H2 exists, they both have to be down here. If we did the same thing over here, what's funny about this one is that it's positively charged. H2 positive has an electron removed. Now it only had 2 electrons, so one of the electrons had to come from that bonding orbital. And by taking an electron out of a bonding orbital, it becomes less stable and its bond order actually decreases. So we can see that here for this 1/2 or 0.5 bond order for H2 positive. And that means it is less stable than H2 itself, which has a bond order of 1. This is calculated through the above equation here, where we put in the number of bonding electrons, which was 2, minus 1, and then 2 minus 1, 2 minus 0, and then take half of that, and we got 1. And here's 0.5. It was calculated by 1 minus 0, and half of that was 0.5. And what about helium? I mean, helium comes in, let's draw it over here. I'm drawing what looks like a little molecular orbital diagram showing you how the molecule forms from the 2 individual atoms. So the 2 individual atoms of helium came in with their 2 electrons. 2 plus 2 is 4. This is a molecular orbital diagram. 2 of them have to go down here and 2 of them have to go up here in anti-bonding. So if you have the same number of anti-bonding as you do bonding, you would end up with a 0 bond order and 0 bond. Now, however, if there's 1 less in here, you might think now I have more bonding than I do in anti-bonding. And sure enough, there is a bond order for He2 plus of 1/2, and that means that molecule could potentially exist. However, He2 does not. This is table 10.5 out of your textbook. It's giving you a heads up on these diatomic elements here. Diatomic, well, lithium we know does not exist as a diatomic element, but can we make an argument? And I wonder if this has been isolated, lithium 2, Li2 diatomically. So when you create the molecular orbital diagram, which is what this is showing right here. This is the molecular orbital diagram for lithium 2+. Now you'll notice what's missing is the sigma 1s star and the sigma 1s. And the reason it's missing is because it's in all of these, and a bonding and an anti-bonding kind of cancel each other out when it comes to bond order. So you don't have to, you can do the calculation, it'll give you the same answer, but you don't have to include it in this, in all of these, since they cancel each other out for the bond order calculation. So let's look at lithium 2. There are 2 in the bonding sigma 2s orbital. So when we do our bond order calculation, we see that there are 2 in bonding minus 0 in anti-bonding, so 0 up here, and half of that is 1. We can continue on for boron 2, and you see that the bond order, by doing that same calculation, I have 2 plus 2 is 4 in bonding minus 2 in the anti-bonding, and half of that, 4 minus 2 is 2, and half of that is 1. So that would say, oh, B2 can definitely exist, diboron, you could call this. Now here's carbon, diatomic carbon. Can that exist? According to this, we have a bond order of 2, which speaks to us a double bond. I hesitate to draw the Lewis structure for it because it doesn't, those two theories don't really overlap. They can contradict each other. And we see that contradiction in O2. When we saw in the very first slide that O2 Lewis structure was like this, and we expected it to be diamagnetic, but it's not. And that paramagnetic means there's a flaw in their Lewis structure. But by doing the analysis of molecular orbital diagram and the bond order, we still see a bond order of 2, which can speak to us a double bond, but we see that some of those are unpaired, and that gives us an explanation for the paramagnetism for O2. If you look at F2, you would get a bond order of 1, and that you would see that they're all paired, and that would be diamagnetic. And sure enough, F2 is diamagnetic by experiment. This table also shows us bond lengths. And we see different single bonds here. I see a single bond here. In lithium 2 and B2, there's a single bond, and in F2, there's a single bond. But they all have different bond lengths. But you wonder, now look at how long this bond is here. It's a very long bond, and long bonds, that's long for a single bond, would not be very stable or be very common to be seen. The bond enthalpies, remember the bigger the number, the harder it is to break that bond, and the stronger the bond. So this is a very low bond enthalpy compared to B2. So B2, I would think, does exist. And then we go to here, we know F2 does exist, and it's stronger bond. So all of this information gives us ideas about the length and the strength of the bonds, as well as their description for a single, a double, or a triple. So N2, I'm going to draw the Lewis structure for N2. And if you look at it, right, we have a triple bond. It looks like it's diamagnetic. They're all paired. And there's that triple bondedness with a really large bond enthalpy. Now this C2 looks like it's got a very large bond enthalpy. Let's do it. Let's do it for fun and draw the Lewis structure. The Lewis structure for C2 would be 8 electrons, and that means you would have a carbon. I wonder, is this possible? It would have to be. And you would have 4 bonds in between there, and that would be pretty strong if it did exist. But it doesn't match our 2 here. That makes me think of a double bond. If we drew that as a double bond, let's play. I need 8 electrons, don't I? So to get 8 electrons, I have 2, 4, 6, 8. Oh, 8. But this is not obeying the octet rule. So you see how these different theories contradict each other. Maybe if I drew all of them in, because I just drew 2, 4, 6, 8, 2, 4, 6, 8. But what about the core electrons? There are 4 of them. Look at that. That makes it work. So if we include the core electrons, but you see how I'm mixing theories, I'm mixing ideas. The Lewis dot structures was the valence, but if we include the core and the idea of bond order, looks like a double bond to me. So you see how that can contradict each other but contribute as well to the understanding of bonding. So let's do an example here of this analysis. This analysis is of nitrogen, which is diatomic, but it's been positively charged, which means that an electron has been removed. And apparently you can prepare N2 positive by bombarding the N2 molecule with electrons. And if those electrons come in, and here's the N2 as we currently know it, say for example, it just steals one of them. One of those fast-moving electrons knocks one of them out, almost like the photoelectric effect. So we would want to, for this example, let's predict the following properties of N2 positive. What's its molecular orbital electron configuration? I call this the molecular orbital configuration. And in that molecular orbital configuration, it's showing the electrons and how they're organized in the molecular orbitals in the molecule. So if you recall, we would see a sigma 1s, and there would be 2 of them. Now let's count electrons before we continue. This is N2, and unlike the Lewis structures, we want all of the electrons. So N2, each nitrogen has 7 electrons total. 7 times 2 is 14. However, we're going to take one away because of that positive charge. So we have 13. Let's see what we can do here. So sigma 1s2, that's the bonding. Sigma 1s star 2. So I've just done 4. Then we go to the next level, which is going to be sigma 2s. And there's a bonding, and there's 2 of them in there. And then there's a sigma anti-bonding, and there's 2 of them in there, and that's the 2s. So far we have used 2, 4, 6, 8 electrons. We need 5 more. Now, how do we fill that up? If you flip back to table 10.5, you will see the order of filling. Now, the order of filling for that is going after the sigma 2s and sigma 2s star. We're going to do pi 2p and pi 2py and pi 2pz. So here's our pi 2py, and there's 2 of them, and then pi 2pz, and these are both bonding, and there's 2 of them. And now I have 1 more to put in, and it looks like that's going to go into the sigma 2px. That's what comes next. And that one is also bonding, and there's 1 of them. So now, let me count up and make sure I have these right. 2, 4, 6, 8, 10, 12, 13 electrons. That's the molecular orbital configuration. And I'll be able to check my work on the next slide. Now the bond order for that bond between the 2 nitrogens, what would that be? We would look at the number of bonding and the number of anti-bonding electrons and take half of that. Normally an N2 has a triple bond in between. But if we take an electron away, I'm thinking it's going to be less than 3 because now it's not going to be as strong. It doesn't have as many in the bonding orbitals. And the magnetic properties, is it going to be paramagnetic or diamagnetic? Well, since we have an unpaired electron, I am thinking it's going to be paramagnetic. And the bond length, how long is the bond going to be compared to relative to the triple bond? Is it going to be longer or shorter? Let's check our next slides. So for the strategy, again, this is example 10.6 from your textbook. You can look at this table, which is what I was looking at on the previous slide when I was working on that molecular orbital diagram and configuration. The stability of the molecule depends on the number of electrons in bonding and anti-bonding. So when I did the molecular orbital configuration, I took note of that. And then from which molecular orbital is an electron removed? Is it removed from a bonding or an anti-bonding molecular orbital? If it's removed from a bonding, your bond becomes weaker. If it's removed from an anti-bonding, your bond becomes stronger. And then as far as your properties for magnetism, if you have unpaired electrons, you would have paramagnetism. If you have all paired, you would have diamagnetism. So in our B2 situation, paramagnetic. C2, diamagnetic. So for our, let's check our work here. This is the one that I just did on the previous page. Sure enough, that looks like the one that I came up with. You had your sigma, and this is the template that I want you to use for your fun sheet. And I kind of stacked these things onto each other. So if I was going to use this template to build a molecular orbital diagram, this is a molecular orbital diagram called MO diagram. And this is the MO configuration or molecular orbital configuration. And that shows where the electrons are, like in a line like this, almost like our electron configurations of our atoms. So I'm going to fill up this diagram with the electrons. And if I was going to do the N2, the one nitrogen, those nitrogen atoms, which have their own electron configurations that were individual to them, was 1s2, 2s2, 2p3, if you recall. And that's where the 7 electrons came from. And then this nitrogen, he also came in with his 7 electrons. Now, the question here is I'm doing N2 positive. So since I'm doing N2 positive, I should not put another one there because I need to create the molecule out of the atoms. Now you might think that the molecule, say we had a tube of nitrogen gas and we zapped it with electricity and one of the electrons was removed from the molecule. So when it was removed from the molecule, it was removed from the highest energy orbital. So I just placed 2, 4, 6, 8, 10, 12, 14, and I did too many. So I am going to erase this one and then put in that one. So here you have, we've placed 13 electrons. Now, since we removed an electron from a bonding orbital, that means that this bond is going to be less stable. So the bond order, it was 3 and N2 alone, but now it is 2.5. So it is less stable. And it's paramagnetic now that it is has an unpaired electron. And the bond length would be longer. And that's what this slide is illustrating, because the electrons in the bonding molecular orbitals are responsible for holding the atoms together. N2 should have a weaker and longer bond. And in fact, it does from 112 to 110, but those are really close now, aren't they? And to check ourselves, because an electron is removed from a bonding orbital, we expect the bond order to decrease. And the N2 plus ion has an odd number, so it should be paramagnetic, which it was. We determined that from our molecular orbital configuration and molecular orbital diagram. So for your fun sheet question and for the last discussion for chapter 10, the goal here is to look at your assigned molecule and do exactly what we just did on the previous slides. Create the diagram from that template that I just showed you on the previous slide, and there's one in D2L for you to show how you fill them up. Write the molecular orbital configuration, just like we did, and here's an example for you for B2. Calculate the bond order, and then comment on the length and strength of the bond. Determine the magnetic properties, and then discuss the stabilities of the molecule, taking into consideration that bond order. So if you go to that discussion board, you'll see which one you're assigned, and then you can post that diagram and the molecular orbital electron configuration in your discussion post for others to help them understanding how this theory works. Now let's go on to delocalization. For delocalized molecular orbitals, that's when you use the word delocalized, that's something that's not confined. So they actually extend over 3 or more atoms. Now, if you recall, we studied benzene in chapter 9 and 10, and the hybridization for each one of these carbons was sp2, and that meant there were unhybridized pi orbitals that made the double bonds. If you recall, benzene can be drawn like this, and it's like alternating single-double, but it can't be because benzene cannot have true single and true double because all the bond lengths are exactly the same. So since they're all exactly the same, the bond must be in between a single and a double, not single and then double and single and then double. And that's why you will see benzene drawn with a perfect hexagon with a circle in the middle, because there isn't really any single and double, there's a mixture. So the electron density, if you remember, there's in an sp2, for all these sp2s, there was a carbon, there was a p orbital that was unhybridized and it had an electron in it. So each one of these have an electron, these unhybridized orbitals, and they are delocalized around here. They don't really know where they are. They're everywhere, but nowhere. So this electron density is above and below, just because of the above and below idea over here. And that's what delocalization is. And delocalization can occur where there are pi bonds. This is benzene again, showing that delocalization. And carbonate also has this delocalization, as well as nitrate and things like that, because I started to draw nitrate, I meant to draw carbonate. Here's a carbonate Lewis structure. If you remember how we would do that, we would have 3 resonance structures, and there was no true resonance structure. They were all right, but they were all wrong. I mean, the true one was a delocalization of that double bond. This could be here, and then that would flip out to generate another resonance structure. So the electron density is above and below, because it seems to me there must be these unhybridized p orbitals that each have 1 electron, and then those can be delocalized throughout there. And it's just kind of this area of delocalized electron density. So these resonance structures were really a description of the delocalization of those pi electrons in the whole molecule, and those molecular orbitals are the ones that are then holding those electrons. These are larger molecules, and it's a little bit more difficult to do the and advanced to do the analysis of molecular orbital diagrams for triatomic or molecules, or even higher than that. So we'll just focus on our diatomics, and so I'll see you in the discussion board about molecular orbital